Now, you could do it the other way, which would be to think about just writing them from the bottom up. And there is one way in which that's more general than what we've talked about. And that's because what we talked about was tree level. And if you wanted to include loop corrections, how do we know that there's not some other operator here that we missed because it just vanished at tree level, for example? We've seen examples where that happens. There's an operator that only shows up at loop level. So we could think about it from the bottom up, even though this is a top-down effective theory, in order to make sure we're not missing anything. And if we wanted to do that, we should enumerate all the possible things, the symmetries, and all that we can use to constrain the form of the operators. So let's enumerate. So there's the power counting, of course. That's pretty simple here. All the powers of one over MQ are being made explicit. And they just tell us what dimension of operator to look for. Just as in our integrating out heavy particles. So we just know the dimension of the fields that we have to put in the numerator from how many MQs we're talking about. There's gauge symmetry, of course, so use covariant derivatives. Very easy to take into account. There's discrete symmetries like charge conjugation, parity, and time reversal, which are symmetries of QCD if we drop the theta term. And we can impose them as well. And again, that's easy. I wouldn't be making a list if there wasn't at least one thing that was hard. And non-trivial. But discrete symmetries are easy. The thing that actually is the hardest is Lorentz symmetry. Well, you say just dot Lorentz indices into Lorentz indices. But you have to ask the question whether we even have Lorentz invariance in this theory. And it turns out that part of the Lorentz group is actually broken by having this heavy quark and doing this type of expansion that we've been talking about. So if you think about the 6 generators of the Lorentz group, the boosts and the rotations, there's a part that I could call the transverse part, which is transverse to the velocity. So in the rest frame, that would be M12, M23, and M13. And those are the rotations. So this is V's like this. So no matter what V you pick, there's always 3 generators that are rotations. And then there's the boosts. And you should think of the boosts as taking V mu and then M dotted into the V and then making the other guy transverse. So we'll need to note it like that. So the new index is transverse, and the rest frame, that's M01, M02, and M03. And so introducing V mu actually breaks the boosts symmetry. And if you like, you could think that the reason it breaks the symmetry is because it gives a preferred frame, which is the rest frame of the heavy quark. If you have a preferred frame, then you've broken Lorentz invariance. So that's bad. And it turns out there's actually a hidden symmetry of this effective theory that partially restores this breaking. And it restores it in exactly the amount that it needs to restore it. That is, it restores it at low energies. And it's called reparametrization invariance. which I'll write once, and then forevermore talk about as RPI, reparameterization invariance. And it's an additional symmetry that we have on V mu itself. So let's go back and think about how we introduced V mu in the first place. So we're saying that V mu breaks part of the symmetry, but how did we decide on what V mu was? How much freedom was there when we defined V mu at the beginning? If we're saying that it breaks it, we should know how much freedom there was, because a freedom to define different V's could restore symmetry, just realized in a different way, and that's what happens. So where did it come from? We had P of a heavy quark, and we split that into two pieces, MQV plus K. But this split into two pieces is arbitrary by some amount. We could move pieces back and forth between here and here, and we would still have the same theory. We have to be careful that we're moving back pieces that don't violate the power counting. And that's what I mean by somewhat arbitrary here, not completely arbitrary. There was a point to doing this because we wanted to separate out the big piece and the small piece, but we could always move a small piece back over here, and that wouldn't change this decomposition. So the invariance that you have is the following. You can take V mu and send it to V mu plus some epsilon mu over MQ, and K mu goes to K mu minus epsilon mu. That moves a piece back and forth between them, and as long as I think that epsilon mu is some parameter that doesn't have a power counting, and i.e. its order doesn't have any MQs in it, it's just something of order lambda QCD, say, then that makes the power counting still true. That was the point of this decomposition. And it allows us to move a small piece back and forth. The small piece is this epsilon. So that's a symmetry, and that's called reparameterization invariance. So we have to make sure that when we construct our effective theory that it satisfies this symmetry if we want it to be a boost invariant, if we want to restore boost invariance to the theory. So this parameter epsilon you can think of as, you could consider it to be a finite reparameterization symmetry, but you don't really have to worry about finite transformations. You can just do the infinitesimal. So we'll think about epsilon mu as infinitesimal. And it has that counting that I put over there. Now v squared was equal to 1, and that's also something we don't want to spoil, but that's easy. We just say that epsilon dot v is equal to 0. And that maintains this condition. So that means that there's three different components of epsilon. Non-trivial components to epsilon. And those three components of epsilon are exactly related to the three boosts here. Okay, we have a three parameter family of transformations. Which are the three components of the epsilon, which in the rest frame would just be the 1, 2, and 3. What do we do? What about the fields? How does the field, the QV, change under this type of transformation? Let me take the field at x equals 0 for now. So v slash on QV, it was equal to 0. And if I do the transformation, then this v slash changes. It becomes v slash plus epsilon slash over MQ. Let me imagine QV changes. It goes to QV plus delta QV. And I have to do that on both sides. Then I can take this. So this thing here is some order epsilon change. Then I can take this equation and I can just solve, so the piece that's order epsilon to the 0, just satisfied, solve for the piece that's order epsilon, and that gives me an equation for delta QV. So rearranging this equation, I find that 1 minus v slash delta QV is epsilon slash over MQ times QV. And this equation has the solution that delta QV is epsilon slash over 2MQ. Remember that epsilon is transverse to V, so if I push a V slash, so if I plug that solution in here and I push the V slash, and I push a V slash through the epsilon, well, then I can push the V slash through the epsilon, let it hit the QV. That's giving a factor of 2 because it anti-commutes. That's this 2 here. And then I would get what I wrote on the right-hand side. So if it's not obvious, check for yourself that that's a solution. So that's how you derive the change to the field under this reparametrization. And so when we talk about operators in the effective theory, we have to worry, how does this symmetry act on them? And it's kind of a non-trivial symmetry. Was not apparent to us when we started, right? Okay. So the full reparametrization is V mu goes to V plus epsilon over MQ. And then if I take QV of x, then that is what I said. There's this epsilon slash over 2MQ piece. This is the transformation, so it goes to itself plus this extra piece. And the fact that I take it at x adds one little slight wrinkle, and it just gives this extra phase factor. And that extra phase factor is exactly what encodes the change of k. So this, if you like, encodes that derivatives should go to derivatives minus epsilon, or in momentum space that k should go to k minus epsilon. Okay, so previously we had a rule for k, but now I've encoded that in this phase. Okay, so that's the symmetry that we should look into. So what does it do? So what this does is it restores invariance under boosts, but only small boosts. The reason that I call them small boosts is because epsilon here had to be of order lambda QCD. It couldn't have been of order MQ. That's what I mean by small. And from the point of view of this theory, this is all we care about. Because we want to remain within the region where the effective theory was valid. The whole setup of the effective theory involved dividing out a large piece into a small piece. If we allow back large pieces, then the game is over, and you wouldn't be formulating correctly the effective theory, because you'd spoil the power counting. Okay, so this is this hidden symmetry called reparametrization invariance. And it's not special to HQET. Anytime you have fields that are labeled by something, you should think about whether there's a symmetry like this. Okay, so that's the entire list of the symmetries that you should consider in order to think about doing a bottom-up approach to HQET. Simple ones, and then there's this one that's a little more complicated. So let's go back and now consider the 1 over MQ operators. In general. And it turns out that there's not any missing operators, that the two operators we have are actually the complete set that you can write down. this dimension using all the properties of the fields. So we didn't miss anything from that point of view. So let me write them down again. And let me write them down in a way where I imagine that radiative corrections have come in as well. And I'll give them some Wilson coefficients, which are generically called CK and CF. That's the standard notation. So this is a Wilson coefficient. And that's a Wilson coefficient. So this is not 4/3. It's Wilson coefficient. The name is the same as the CF that is 4/3, but this is a little CF, not a big CF. So if we want to, so it's gauge invariant, it has the right parity, et cetera, we should worry about the reparameterization invariance. So let's do that. So at lowest order, it's the phase is what changes. And the leading order Lagrangian is invariant because v dot epsilon is 0. So at order mq to the 0, since v dot epsilon is 0, you don't get a leading order change. So our Lagrangian was invariant. This invariance, this reparameterization invariance, mixes orders. It connects orders in the expansion. There was a term that was order 1, which is this piece, and there's a term that's order 1 over mq. So the symmetry is actually making a connection between leading order and subleading order operators. So we could ask about this delta L0, and there will be a piece at order 1 over mq. So let's just write out all these things. Transforming everything. This is our leading order Lagrangian. After imposing the field change as well as the v change, the v dot d becomes this, and the field becomes that. So there's 3 things here that are being changed. Expand this out. Use things like 1 plus v slash over 2, epsilon slash 1 plus v slash over 2 is equal to epsilon dot v is equal to 0. Simplify, do some Dirac algebra, and you can boil this down to something simple, which is that the entire change is just an epsilon dot d over mq times qv. And if you look at this, it has to cancel against something that's order 1 over mq. And if you look at the terms that we had at order 1, which are 1 over mq, there was a kinetic piece. We called it kinetic energy piece. And if we do the change there, there is a contribution from the phase in this case because we had transverse derivatives. So we can have epsilon dot d transverse. That's non-zero. And if you go through the leading order change to this guy, as well as the guy that's the magnetic guy, you find that the magnetic guy is 0 at this order. It's non-zero at higher orders, but at this order it's 0. And the kinetic guy does have a transformation. It has exactly the same form as this guy here. If epsilon's dotted into the d, then it's a d transverse. But this guy has a Wilson coefficient. This guy doesn't. So in order for these to cancel, you actually learn something non-trivial. The symmetry teaches you something non-trivial about the subleading Lagrangian. That Wilson coefficient has to be 1 to all orders in perturbation theory in order for the symmetry not to be violated.
But you are enforcing the symmetry.
Yeah. So the symmetry is boost invariance, and it seems like a reasonable symmetry to impose. Yeah. These small boosts. So as long as your scheme and your regulator don't break the symmetry, which is always something that you have to worry about in general, then this guy is 1 to all orders. Okay, so if you did something like dimensional regularization and you thought you should calculate this guy, you just find that it would be 1. And you'd wonder, well, why is that? It's the symmetry that tells you it's 1. Okay, so you don't have to figure out that guy. The other guy, which we've called CF, you do have to figure out because it wasn't constrained. And at lowest order, the other coefficient is not constrained in this way. And so it does get an anomalous dimension. And so we could calculate it. It's a good homework problem. You may see it on a future homework set. And there is an anomalous dimension, and when you solve that anomalous dimension, you're again getting something that's a ratio of alphas to some power. In this case, it's a non-abelian power. It's the adjoint Casimir. Okay, so that guy does have an anomalous dimension. And I think we'll stop there today, and we'll talk more about power corrections and sort of phenomenology of them and how we can make non-trivial predictions from them next time.